Welcome to the new lecture. In this lecture, we will discuss about the boundary conditions for E and V and the idea of electrostatic potential energy and some idea about the capacitors and its capacitance and how much energy is stored in this capacitor. Before that, I will discuss or I will just tell you about what is the relation between V, E and rho. In the last lecture, we had derived all those such equations, but diagrammatically I am going to represent an equation connecting V, E and rho, which is the volume charge density. So, this is that diagram rho, V and E, which makes the three corners of an triangle. So, here V and E is equal to minus del V. This is the connection between E and V, and another equation E is equal to 1 by 4 pi epsilon 0 integral rho d tau by r square into r cap. And what about V and rho? V and rho, V is equal to 1 by 4 pi epsilon 0 integral rho d tau by r. This is the connection between rho and V, and similarly rho and E and V and E. And we know that there is another relation between E and V, which is equal to V is equal to minus integral E dot dl. By this you can find out what is V in if you know E, and by this equation if you know V you can find out what is E. Similarly, there is a connection between V and rho. If you know rho, you can find out V. Similarly, you can find out what is del square of V, which is equal to rho by epsilon 0. If you know V, you can find out what is rho, which is equal to epsilon 0 rho V square. And here also you can write the Gauss's law. You can find out rho if you know the electric field, which is equal to epsilon 0 into del dot E. This is the connection between rho, V and E. Using this equation or using this diagrammatic relation, you can find out, if you know this quantity V, you can easily find out what is E. If you get E, you can find out rho. These are the three main quantities needed in the case of an volume charge distribution. You can find out whatever physical quantity you need. So, this is the main, we can call it as the backbone of the electrostatics. These four, not four, the 6 equations. Okay. Now, we will discuss about the boundary condition. Boundary condition. So, what is actually the boundary condition? This boundary condition will tell you how the electric field is varying between two boundaries. So, this is the boundary here, this is the boundary, and we want to find out what is the electric field in the upper part and electric field at the down part of this boundary. So, this is the, this AB represents the boundary. So, this upper electric field is divided into two parts, which is equal to two components. It is its perpendicular component, E perpendicular up component and E parallel up component. With the parallel component means the component which is parallel to this boundary. Similarly, and this is, you can split into two surfaces which is equal, two components which is equal to E perpendicular down component and E parallel down component. E parallel down component. How will you choose this parallel component or the down component? For that, you should actually consider a pillbox, Gaussian pillbox pillbox. With respect to this pillbox, we will talk about this boundary condition. So, I am naming it as P, Q, R, S and P, Q, R, S, and this pillbox has a surface charge density of sigma coulomb per meter square. Sigma coulomb per meter square. So, what is the change in the electric field? The change in the electric field delta E is equal to E up component minus E down component. If the up component of electric field is equal to the down component of the electric field, then that means the electric field is continuous across that boundary. If something is changing across that boundary, then the electric field is non-continuous. So, we will check in which of these components are continuous and which of these components are discontinuous in this boundary or in this interface. So, I told you, right, E up can be split into 2, which is equal to E perpendicular up plus E parallel up. Similarly, E down component is equal to E perpendicular down plus E parallel down. So, we know that you can club these equations and you will get an expression for delta E, where delta E is equal to E perpendicular up plus E parallel up minus, for the down component, E perpendicular down plus E parallel down. So, I can club the perpendicular components together, that will give you E perpendicular up minus E perpendicular down plus E parallel up minus E parallel down. Now, the electric field components has been split into 2 parts, actually the perpendicular part and the parallel part. Now, we will check whether the perpendicular part is continuous or the parallel part is continuous. So, first of all, we will discuss about the perpendicular component, whether this perpendicular component is continuous. Now, consider this wafer thin pillbox has a thickness tending to 0. That means, this thickness is very small and about a charged sheet which acts as a boundary, and this is a charged sheet which has just like this has a charged sheet, and this is that boundary, and these 2 point, this is the 2 interface, this is the upper part and this is the down part. So, how we will check whether the E perpendicular up component is continuous? So, we know that for an thin sheet of charge, the electric field produced was E is equal to sigma by 2 epsilon 0 into n cap. I think you remember this equation we have derived using the Gauss's law for a thin charged sheet. E is equal to sigma by 2 epsilon 0. So, what about E perpendicular component? E perpendicular component is equal to, for this thin sheet of charge, E perpendicular up component is equal to sigma by 2 epsilon 0 into n cap. Remember, I am setting this n cap in this direction. So, what about E perpendicular down component? In the lower part also, for the down component part also, E perpendicular down, E has the same magnitude. If the surface charge density is sigma, E perpendicular down is equal to sigma by 2 epsilon 0 into not n cap, because we have set n cap in the up direction. So now the n cap will become minus n cap. So which is equal to minus sigma by 2 epsilon 0 into n cap. So therefore E perpendicular up minus E perpendicular down is equal to sigma by 2 epsilon 0 minus of sigma by 2 epsilon 0, which is equal to sigma by epsilon 0 which is into n cap. So not the n cap, which we set it into the magnitude, which is equal to sigma by epsilon 0. That means E perpendicular up minus E perpendicular down is discontinuous at the boundary. That means they are varying with an amount of sigma by epsilon 0. If you set the I am talking about this magnitude, if you want to tell in the vector direction, in the vector form, you should write it as n cap. Initially I told about the magnitude, now I am talking about the direction is not, if the direction is not depending, then E perpendicular up minus E perpendicular down is equal to sigma by epsilon 0. Now this become sigma by epsilon 0 into n cap, become sigma by epsilon 0 into n cap. That means the perpendicular component is discontinuous at the boundary. And what about the parallel component? So to determine the parallel component, and we know that the electric field is an conservative force field. We are using such an idea to convey the idea of the parallel boundary condition for the parallel component of E. And we know that closed integral E dot dl is equal to 0 for a conservative force field. So according to this closed integral E dot dl is equal to 0, this is a closed path which is equal to PQRS. I can take this path as PQRSP. Since I want to make it as a closed path, I should write it as PQRSP. Now it became a closed path, P to Q, Q to R to S, and again from S to P into integral E dot dl is equal to 0. But I can split this integral into from integral PQ, the path along the path PQ E dot dl, plus the path integral QR into E dot dl, plus integral RS in E dot dl, plus integral SP E dot dl is equal to 0. Now I completed one complete cycle, PQ to QR to RS and to SP. Now what about these two integral, the second and the fourth integral, second and fourth integral? We know that, and I initially told you that this thickness is very, very small. This integral will vanish. This integral will vanish, and this is actually the parallel component of E. Which integral? Which is PQ and RS. And remember, this PQ is in this, if PQ is in the forward direction, then RS is in the reverse direction. So while taking the dot product, this will become, integral PQ will become E parallel up component, this is the parallel up component, into dl, which is in the opposite direction. So I can write it as dl cos 180 degree plus, and this two will, this first, second and fourth integral will become 0 because its thickness is very small, and this can be approximated to 0. Now, what about integral rs into E dot dl? Integral rs into E dot dl will give you integral E parallel down component dl cos 0 degree, where this angle lies between the direction of the electric field and in which direction it is moving, which is the dl, the angle between the dl and E. Now, E parallel plus E parallel up dl cos 180 plus E parallel down cos 0 degree is equal to 0. That means minus of, because cos 180 degree is minus 1. So, E parallel up plus E parallel down is equal to 0. That means E parallel up is equal to E parallel down. That means the parallel component of electric field is continuous at the boundary. Parallel components are continuous at the boundary and E perpendicular components are discontinuous at the boundary if there is an surface charge density. What about if the surface does not contain any charge density? If sigma is equal to 0, what about the perpendicular component? If sigma is equal to 0, then E perpendicular up is equal to E perpendicular down. If the surface is free of charge, then the perpendicular component also is continuous at the boundary. Now, for the potential, what is the boundary condition? Before that, we can club these two equations. We know that delta E, what is our main equation? Delta E was main equation, delta E is equal to E up minus E down, but E up, we know that for E up, which is equal to E perpendicular up minus E perpendicular down minus E parallel up minus E parallel down. This was our equation. So, what we will get it is E perpendicular up minus E perpendicular down is equal to, we will get it as sigma by epsilon 0 into n cap plus 0, which will give you sigma by epsilon 0 into n cap. This is the boundary condition for E if the surface charge density is present. If sigma is absent, then sigma is equal to 0, then delta is equal to 0. And what about the boundary condition for the potential V? This can be easily achieved by using the equation for the potential. What was the equation for the potential? For the equation for the potential, V is equal to minus integral E dot dl. So, we are choosing the path. So, according to this equation, this has a boundary which is equal to PQ, and we are taking the path along the PQ and along the path RS. So, V is equal to integral minus integral P to Q E dot dl, which is equal to from R to S E dot dl. The potential at the upper part and at the lower part. So, the V up minus V down part will give you the idea of the relation between the boundary condition for the V. So, since these potential are at the same, because V up is equal to V down component, we will get it as the potential is the continuous over the upper part and the lower part of that boundary. And what about the gradient of the potential. According to the gradient of the potential also we can find out, because the electric field is nothing but the negative gradient of the potential. From this expression we know that E up minus E down is equal to minus of V up minus del of V down. What is E up minus V down? Which is equal to sigma by epsilon 0 into n cap, which is equal to minus of del V up minus del V down. Del V up minus del V down. This is the boundary condition for the gradient of the potential. So, V is equal to minus del V, and there will be an extra minus sign because this contains a minus, which is equal to minus. So, which is equal to minus sigma by epsilon 0 into n cap, which is equal to minus of del V up minus del V down. So, we can write it as sigma minus sigma by epsilon 0 into n cap, which is equal to del of V up minus del of V down. V up minus V down. So, I can club and write the 4 equation for the boundary condition for E and V. That means E perpendicular up minus E perpendicular down is equal to sigma by epsilon 0 into n cap, and E parallel up minus E parallel down is equal to 0 because they are continuous at the boundary, and similarly V up minus V down is equal to 0, and V del gradient of V up minus gradient of V down is equal to minus sigma by epsilon 0 into n cap. These are the boundary conditions for E and V. So, boundary condition for E and V, which will give you the variation of the up E when it passes through a boundary. Now, we will discuss what is the work done in an electric field. Work done in moving a charge in an electric field. So, when a charge Q is moved from a point A to point B, where this point A and B is itself in an electric field produced by another charge Q dash. So, I will represent this diagrammatically as this is the source point, which I am represent as Q dash. To a point, I am moving the charge from point A to point B, and I am moving this charge Q at a distance dl. So, what is the work done in moving this charge? The force acting on the test charge Q, capital Q, is, we know that from our first lecture we have learned this as F is equal to QE. F is equal to QE. So, what is this E? This E is the electric field produced by this source point Q dash. So, how much work I should do to push this charge to a displacement of dl. So, which is equal to dw is equal to minus f dot dl. Since I am doing the work against the field, I should put this negative sign. So, I am substituting this value of f here, dw is equal to minus of qe dot dl. So, the total work done is equal to integral dw is equal to minus q into integral e dot dl. Integral e dot dl. So, if I want to move it from point A to point B, should put the limit from point A to point B, which is equal to minus q into integral a b e dot dl. What is minus of integral? I am taking this q here and putting this minus here. What is minus integral a to b E dot dl? Minus integral a to b E dot dl is nothing but the potential difference. The potential difference. So, I can write it as q into Vb minus Va. Q into Vb minus Va. So, in general, I can write it as the work done in moving a charge q in an electric field is nothing but q into Vb minus Va, where Vb minus Va is the potential difference at that points. If there is no potential difference, then the work done is equal to 0. We don't need to do any work to move a charge. So, Vb minus Va is equal to W by Q. So, the potential difference between any 2 points is the work done in moving the unit positive charge between the 2 points. So, this is the relation between the work done and the potential difference. So, what about the potential? The potential, if you set one point at infinity, I can write W is equal to QV. This is an important relation connecting this potential and the work done. And this work done, now we will call it as the potential energy. The potential energy, and it is represented by the letter U. So, U is equal to Q into V. This is the potential energy, the expression for the potential energy, and its unit is SI unit is joule. So, in all cases we will discuss, we will tell about we will discuss about a physical quantity, and for a single charge, then what we were doing was we will do it for a continuous distribution of charges or for a charge distribution or something. In this case also we should find out what is the energy of a discrete charge distribution. For a discrete charge distribution, the work done should be in the form of Q into V, right. So, what is this Q? This Q is lots of charges assembling together to form a charge distribution. So, initially consider on this board there is no charge or there is no field. So, I want to assemble n number of charges on this space. So, I am taking a charge q and I want to assemble this charge at this point P, at this point P. So, what is the work done? We have the expression W is equal to Q into V. The general expression is W is equal to Q into V. But what is the potential initially, the potential at this point P? Initially there was no charge, so the potential is equal to 0. That means W, I am taking the first charge Q1 and I want to take this first charge to the point P, or I am naming it as P1, take it as P1. So, what is the work done to assemble this charge at the point P1? At this point P1, W is equal to 0. Why? Because the potential at the point Vp1, that is the potential at the point P1, we will name it as potential at the point P1 is equal to 0. The potential at the point Vp1 is equal to 0. Why? Because there was no charge. So, W1 is equal to Q1 into Vp1, where Vp1 is equal to 0. So, Q1 into 0, that is W1 is equal to 0. W1 is equal to 0. Now, I took this Q1 and I am keeping this charge Q1 at the point P1. Now, I want to set another charge at the point point P2 here. I want to put this point, say P2. So, what is the position vector? I will represent the position vector as R21, the vector R21. So, what is the work done to assemble or to bring a charge to the point P2? to bring a charge Q2 to the point P2, I want to bring this charge to the point P2, I should do a work which is equal to W2, which is equal to Q2 into the potential at the point P2. Is the potential at the point P2 0? No. The potential at the point P2 is not 0 because there is a charge at P1. So, there will be a field produced by this charge Q1. So, the potential is not at all 0. So, what is the potential at the point P2? The potential at the point P2 is not 0, which is P2, the potential at the point P2 is equal to 1 by 4 pi epsilon 0 Q1 by R modulus of R21, modulus of R21. Why? Because the potential at this point is due to the electric field produced by the first charge Q1. So, the W2 will become W2 is equal to 1 by 4 pi epsilon 0 Q1 by R modulus of R21 into Q2. So, this is the work done in assembling a charge Q2 in the presence of another charge Q1, another charge Q1. So, I can write it as W2 is equal to 1 by 4 pi epsilon 0 Q1 Q2 by modulus of R21. Now, I want to assemble another charge Q3. I want to assemble another charge Q3 at a point P3. What is the work done to assemble this charge? If you check, you can see that the potential at the point P3 is due to the potential due to the charge Q2 and similarly the charge Q1. So, V at P3 can be written as V at P3 can be written as Vp3 is equal to the potential 1 by 4 pi epsilon 0 due to the charge Q1 by, I name it as R31, the vector R31 and now the vector R32. So, Q1 in Q1 divided by R3 modulus of R31 and plus 1 by 4 pi epsilon 0 Q2 by modulus of R32. Why? Because Vp3 is the sum of Vp Vp3 is the sum of charges assembled at the point P1 plus the charges assembled at the point P2. So, this is Vp3. So, the work done W3 is equal to Q3 into Vp3. So, which is equal to, I can write the expression for W3 as 1 by 4 pi epsilon 0 Q1 Q3 by R3 modulus of R31 plus 1 by 4 pi epsilon 0 Q3 Q2 by modulus of R32, modulus of R32. Since this we are taking the modulus, I can write R21 is R12. I just inverse the notation for the position vector. So, I can write W3, W1 as 0, W2 as 1 by 4 pi epsilon 0, Q1 Q2 by R12, W3 as 1 by 4 pi epsilon 0, Q1 Q3 by modulus of R13 plus 1 by 4 pi epsilon 0 Q3 2 Q3 by modulus of R2 3, modulus of R2 3. So, this is the potential at the work done to bring a charge at the point P3. So, what about if I want to similarly I want to find out what is the work done in assembling a fourth charge? It will be Vp4 will be V14 plus V24 plus V34. The extra term will come because there will be another charge P3. So, that charge will experience a potential due to this in 3 charges, that is Q1, Q2 and Q3. So, in general I can write it as, if there are 4 charges I can write it as 3 charges I can write it as the total work done is equal to W is equal to W1 plus W2 plus W3, and if there are 4 charges then it is W3 plus W4. So, what about W4? W4 will be, you can just look into the board and you can write the expression for W4. W4 will be equal to 1 by 4 pi epsilon 0 Q1 Q4 by modulus of R14 plus 1 by 4 pi epsilon 0 Q2 Q4 by modulus of R24 plus 1 by 4 pi epsilon 0 Q3 Q4 by modulus of R34. So, this is the work done to assemble the fourth charge. So, what is the total work done? The total work done is W1 plus W2 plus W3 plus W4. So, I can club this 4 equations and I will write it as W is equal to 0 plus 1 by 4 pi epsilon 0. This term represents the W1, which is equal to 1 by 4 pi epsilon 0 Q1 Q2 by modulus of R12, this is W2 plus 1 by 4 pi epsilon 0 Q1 Q3 by modulus of R13 plus 1 by 4 pi epsilon 0 Q2 Q3 by modulus of R23, and this represents the W3 plus 1 by 4 pi epsilon 0 Q1 Q4 by R modulus of R14 plus 1 by 4 pi epsilon 0 Q2 Q4 by modulus of R24 plus 1 by 4 pi epsilon 0 Q3 Q4 by modulus of R34. So, is there any similar terms? Yeah, not similar terms. You can club this term Q1 Q2, Q1 Q3 and Q1 Q4. Then again Q2 Q3, Q2 Q4 and Q3 Q4. So, you can, in general you can write into an single equation, which is the total work done W is equal to 1 by 4 pi epsilon 0 sigma Qi Qj, sigma Qi Qj divided by modulus of Rij. So, I should put the condition that I is not equal to j. I is not equal to j and I runs from 1 to n, and similarly j also runs from 1 to n. But this is incomplete, because if you take the summation you will get it as Q1 Q2 and you will again add it as Q2 Q1, both are same. So, that you will get it and double the term of the work done. So, you should put an half to reduce into that exactly into the real work done, because this summation will double the term. So, and in addition to that I am sorry for removing that additional term I am putting an half, which is equal to half into 1 by 4 pi epsilon 0 sigma I is not equal to j, j is equal to 1, I is equal to 1 to n Qi Qj and modulus of Rij. This is the work done in assembling n number of charges, discrete n number of charges to a point to a region, not at a point, to a region. So, if you want to remove that, or you can neatly write this equation again into an symmetric form, or to, if you want to derive any other equation or to derive any other concept for the continuous charge distribution, you can write like this also: W is equal to half into sigma qi, where I runs from 1 to n. You are just separating the summation, which is equal to sigma j is equal to 1 to n and j not equal to I, q j into r I j modulus of r I j into 1 by 4 pi epsilon 0. So, what is this term actually? 1 by 4 pi epsilon 0 q j by sigma q j by r I j. This is nothing but which is equal to half into sigma I runs from 1 to n q I into v of p I, v of p I. So, this is the general expression for the work done to assemble n number of charges. So, if it is a continuous distribution, then the potential itself, everything will become a continuous distribution of charges, and the potential will become sigma Vpi will become V, and sigma Qi will become dq. So, we can write it as W for the continuous charge distribution. W is equal to half into integral dq into V. For the, if it is a continuous charge distribution, I can write W as half into integral dq into V. In the case of a continuous charge distribution, W is equal to, I told you W is equal to half into integral dq V. Now, we will write about what is the work done for an volume charge distribution and for a surface charge distribution, similarly for an line charge of distribution. So, I will focus on the volume charge distribution. So, for a volume charge distribution, I can write it as integral dq. I can, it is a very simple equation which is equal to integral dq v, where I can put dq as integral rho v into d2, where rho is the volume charge density. And similarly, what about for a surface charge density sigma, the work done is equal to half into integral sigma v into dA. And for a line charge density, linear charge density lambda, W is equal to half into integral lambda into V d L. These are the three equations that may be needed to solve the numerical problems, and this represents for the volume charge, surface charge, and for the linear charge density. Now, we will check or we will derive what is the expression for the energy stored in an volume distribution of charges. It is a very important expression, and some physics lies inside the equations in which we are deriving. So, the main idea to derive the expression for the energy stored in an energy stored for a volume charge distribution is this expression. From this expression, we will start and we will apply the idea of Gauss's law to get into what is the total work done. So, the work done or the expression for the work done or the energy stored in an volume distribution of charge. So, we will begin from this equation. W is equal to half into integral rho v d2. And by Gauss's law, we know that del dot E is equal to rho by epsilon 0. That means rho is equal to epsilon 0 into del dot E, right. So, I am substituting this value here, that is equal to W is equal to half into integral rho is epsilon 0 into del dot E V d2, del dot E V d2. How will you solve this integral? How can we solve this integral? Is another question. So, we will go back to the earlier mathematics, which we will apply the product rule for the divergence. Do you remember this equation? Del dot E V is equal to, what is del dot E V, which is equal to del dot E into V plus V E dot del V, E dot del V, E dot del V. So, is there any similar term here? Yes, here is that term. So, I will take this term here, del dot E V minus E dot del V is equal to del dot V, E dot del into V. So, I can substitute here W is equal to half into integral epsilon 0 into del dot E V minus E dot del V into d2. I will separate this integral and I will write it as W is equal to half into integral epsilon 0 del dot E V d2, del dot E V d2 minus half into integral E dot del V into d2, E dot del V into d2. Both are volume integral. What about del V? We know that del V is equal to minus E. So, I can write W is equal to half into integral, or epsilon 0 I will take out, which is equal to del dot E V into d2 minus half into integral E dot minus E d2. Both are vectors. So, this minus and this minus will become plus, right. So, which is equal to half epsilon 0 into integral del dot E V d2 plus half into, there is an epsilon 0 here, I forgot, right, which is equal to epsilon 0 into integral E square d2. What about this term, the first term, del dot E V d2? I can apply the Gauss's divergence theorem here. If I apply the Gauss's divergence theorem, this W will become W is equal to half into epsilon 0 into, this volume integral will become the surface integral, which is equal to E V dot dA plus half into epsilon 0 into E square d2. Since E is a vector and V is a scalar, I can rewrite this equation as W is equal to half into integral epsilon 0 into V into E dot dA, E dot dA plus half into epsilon 0 into integral E square d2, half into epsilon 0 square E square d2. So, half into integral the total work done, half into integral rho v d tau is equal to half into integral epsilon 0 v e dot dA plus half into epsilon 0 e square d tau. E square d tau. So, if you integrate this term, what will happen is this term is a variation of 1 by r square. If you integrate more and more and more, this term will vanish, and around the whole space only this term will only will survive, which is equal to W is equal to epsilon 0 by 2 into integral E square d tau. So, this is the expression for the energy stored in terms of an electric field, the intensity of electric field, because E dot T will give you, E square will give you the intensity of the electric field. So, this represents the energy stored in terms of intensity of electric field. So, what is the energy density? The energy density is defined as the energy stored per unit volume. So, the energy stored per unit volume is called, the energy density is nothing but, you can easily derive it as epsilon 0 half into epsilon 0 E square. So, we will check how we will derive that equation. From this equation you can easily derive that energy density. So, energy density is energy stored per unit, energy stored per unit volume. So, energy stored is half into integral rho v d tau, and per unit volume is integral d tau, which is equal to half into integral into rho v d tau divided by the total volume v. This is the total volume, I will name it as small letter v. But we know that energy density is, the energy stored is nothing but half into epsilon 0 into E square integral E square d tau divided by the total volume v, which is equal to half into epsilon 0 into E square into the small volume v divided by the volume v, and this v and v will go. So, the energy density is equal to half epsilon 0 E square, half epsilon 0 E square. So, this is an useful equation in electrostatics, and the energy stored in the charged distribution itself. So, all this work done and the potential energy and the energy density will help you to calculate how much electric field is produced, and or since this electric field itself is the intensity of the electric field. So, we can find out what is the energy density. So, this equation for electric field density is a useful equation in electrostatics, also useful for the electromagnetic wave theory of electric field. So far we have discussed the idea of potential energy and boundary conditions, electric field and electric potential. The parallel component of electric field is continuous at the boundary and perpendicular components are discontinuous. Finally, we discussed the energy stored in an electric field. Hope this session was useful for you. See you next time. Until then, goodbye.